Hi, in this video we're going to talk about curvature. Curvature is a measurement of how curvy a curve is. So if we look at a curve, here's my microphone cable, there are certain parts of this curve that are more tightly curved than others. If I look at this part up here, it's relatively straight. It's like a straight line. So that's something that we would describe as having curvature 0, or approximately 0. It might have a little bit of curvature. As we get to this part, though, I can see that it's really curving a fair amount. So here we have a non-zero amount of curvature. And if I make it curve really tightly, something like this, that's a lot more curvature. Right? Try to get that behind something bright where we can see it. Right? So we want to have a way to measure this mathematically. How do we quantify the amount of curvature here? So let me show you a curve in 3D and see how we can make sense of this. All right, well, here we have a curve in 3 dimensions. The curve itself is one-dimensional, but it's in 3 dimensions. And so you can see this is the curve. Now I want to find a way to measure how curvy it is. Well, one way to do this is to imagine a circle sitting up next to the curve. And we want to find the circle that sits against the curve with the best fit. So you can actually do this. I'm using a program called CalcPlot 3D, and it's written on the top here. It's written. I can't say it, so just read it. It's a free website you can go to and do this yourself. And one of the things you can do once you make a space curve, a vector-valued function, a space curve, you can turn on osculating circle. And the osculating circle is the circle that I was just describing. It is the circle that best fits the curve at a point. So if I rotate this around, you can see my curve there. I'm at a certain point on the curve. And that circle is butted right up against the curve. Right? That's the best fitting circle. If I were to make that circle smaller, it kind of would have a little bit of gap between itself and the curve. And if I made it bigger, it would kind of extend through the curve and be too large. But you can find a circle that is just right. And this is the circle that we're going to use to define curvature. Now you see, as I move along the curve, the circle changes size. So the size, in other words, the radius of this circle, should have something to do with the curvature of the curve. Now, if the curve is more tightly curved, then what happens to the circle? Well, the circle gets smaller, right? So a small circle means more curvature. And if I move out to the more flat region of the curve, where the curve flattens out, you can see the circle gets quite large. So the curvature is actually inversely proportional to the radius of the circle. In fact, we define the curvature to be the reciprocal of the radius. It's 1 over r. That's the curvature. So what we do to compute curvature is we find the circle, we compute its radius, take 1 over that, and that's the curvature right there. But let's find out how to do this mathematically so that we can do it using a little bit of calculus. Okay, so what we're going to do is we're first going to start by talking about something called the unit tangent vector. The unit tangent vector of a curve r of t. And it's denoted a capital T. And we know how to get a tangent vector to the function r of t. We just take its derivative. That will be tangent to the curve, but it won't be unit length. So how do we get it to be unit length? We divide by its length. And that will make its length 1. And so that's very simple. That's how we get the unit tangent vector. And we're going to use this to define curvature. Curvature is denoted by the Greek letter kappa. It's like a little k with curly legs. It's like a little capital K with curly legs. And it depends on where we are on the curve, so it will depend on t. And it is given by the ratio of the magnitude of the derivative of the unit tangent vector divided by the magnitude of the derivative of the vector function. Now, yes, t has unit length, but we don't know that t prime has unit length, and so don't think that this is going to be 1. Now, we said that the curvature was the reciprocal of the radius of the osculating circle. Why does this give that? Well, that's for another video. I'm not going to explain that here. But I do want to explain something else. I want to explain another expression for the curvature, which will be useful for us. And it will work provided the curve is a three-dimensional vector curve. Okay, so if it is three-dimensional, then the expression can also be written like this. Now you can see why it needs to be three-dimensional, because it involves a cross product. We can only take cross products of three-dimensional vectors. And I want to go through the proof of why these two formulations are equivalent. And the reason I want to do that is because the process of proving it uses some observations which were going to be useful for us going forward. Okay? So how do we prove this part here? Let's write down a proof of this. Well, we need to compute r prime and r double prime and then take their cross product. So when I do this, I'm going to write down these guys without writing the of t, and I'm also going to drop the vector symbol, because otherwise my hand's going to get tired. All right? So keep that in mind. I'm not going to write the of t, I'm not going to write the vector symbol, but otherwise r is this space curve and t is going to be the unit tangent vector. Well, okay, so how do we write down r prime? Well, we can get that from our expression right here, right? Just multiply both sides by the denominator here, and we see that r prime is just the magnitude of r prime multiplied by the vector t. And if we want to get r double prime, we can just differentiate this. Now this is scalar multiplication. This is not the dot product, because this is a scalar and this is a vector. But for scalar multiplication, we have the product rule. It holds for this scalar multiplication. So if I want to take the derivative, I just use the product rule. There we go. Now what do I want to do? I want to take the cross product of those two things. So let's do that next. So I'm going to take the cross product of this thing with this. Now the cross product follows the distributive property. So I can just take the cross product of these two first and then these two and add them together. So let's do the cross product of these two terms. When I do that, I can just bring the scalar multiples on the outside. Okay, now let's do the cross product of these two. Again, bringing the scalar multiples on the outside. All right, what do we have here? Well, if you look at this first term, it looks kind of messy, but then it's t cross t. If you take a cross product of a vector with itself, you get 0. So that's completely gone. That's great. So really, this whole thing just simplifies to this. Great. Now, we want to compute the magnitude of that cross product, so let's do that. Okay, so we need to somehow figure out how to compute the magnitude of t cross t prime. Well, we know a nice formula about the magnitude of a cross product, provided we know the angle between the two vectors. And that says that we multiply the magnitudes of the vectors together, multiplied by the angle between them. So let's write this down. Multiplied by sine of theta, where theta is the angle between these two vectors. Now, do we know this angle? Well, this is the part where we have to be a little bit clever. And this is one of the tricks that we want to know about. We may use this trick in the future. What's the angle between these two vectors? Well, what I want you to observe is what we get if we take the derivative of t dotted with itself. Now, it's not obvious that we'd look at this, but I want you to look at this. So if I take t and take the dot product with itself and then take the derivative, what do we get? Well, we use the product rule. The product rule applies to dot products. So I get t dotted with t prime plus t prime dotted with t. And because dot product is commutative, this is the same thing as twice t dotted with t prime. All right. Well, that means that if I just divide both sides by 2, I can see that t dotted with t prime is equal to 1/2 of this. But wait a minute. Remember, any vector dotted with itself gives you its magnitude squared. But if t is a unit vector, its magnitude squared is equal to 1. So this is always equal to 1. It's a constant. If I'm differentiating a constant, I always get 0. So now I know that t dotted with t prime is 0. Aha! If two vectors dotted together give me 0, that means those vectors are perpendicular. T and t prime are orthogonal. That tells me that theta is equal to 90 degrees. That tells me that sine of theta is equal to 1. Great. So now we have an expression for the magnitude of our cross product, which we wanted. Okay, well, to see what this thing becomes, well, we just need to divide by the magnitude of r prime cubed. Let's do that. So I'm going to divide both sides of this by the magnitude of r prime cubed. And what do we get here? Dividing this by r prime cubed cancels these, leaves an r prime, a magnitude of r prime in the denominator. But what do we also know? We know that the magnitude of t is 1 because t is a unit vector. Now, what is this? This was kappa. This was curvature. And so this proves the statement that we wanted to prove. So we have finished our proof. And so the punchline here for this video is that we have both of these expressions that we can use to compute curvature.